We see you.
You see me? You don't.
Yeah, we
you don't.
see your video.
Oh, but you don't see my desktop.
Are you gonna?
Not yet.
So today, and everyone should either have the handouts because I gave them out in class, or if you don't have the handout, it should be on Moodle. But we're going to do lecture 8-1 power measurements, and this is actually from Dr. Gregg's notes. It's not actually in your textbook, but there is something about power measurements in your textbook, and it's pretty similar. So to measure power in a circuit, we use something called a wattmeter. A wattmeter is used to measure real power, and it is a 3-terminal device, and it is comprised of a voltage module and a current module, which makes sense because we know that power equals voltage times current. So if you have a source and a load, what you do is you put the device that's the current module, which would be like an ammeter, in series with the source. And then you put a device that is like a voltmeter in parallel with the source and load. And so then if you want the power, then you just measure this current and voltage and you put them together in the wattmeter and it spits that out. So notice that the current module's positive terminal is connected to the source and its negative terminal is connected to the load, and the voltage module is positive on top and negative on the bottom. And like I said, when you combine those two together, it's just a voltmeter and an ammeter. And when you put them together, it becomes a wattmeter, which is used to measure power. And it gives you that quantity. So on to page 2. I'm going to make this a little bigger because I don't like the continual scrolling. That's annoying me. So here's what this looks like on the circuit again, where you have the wattmeter here in the middle, the 3 terminals. So if I bring in that current value, I bring in that voltage power value, it gives me my power in watts. So we know if it's the power in watts, then that is the average power, right? The average power. And that S, the product of the voltmeter and the ammeter readings, gives me the apparent power. Okay, so I haven't written on this thing in a long time, so let's see if this is actually going to work. So that means the magnitude of S, right, is just volts times amps. And then we know that the real power is just the wattmeter reading, because that's the same as VI times the cosine of theta, where we know theta is theta V minus theta I. So then the reactive power is the square root of S squared minus P squared. So as long as you have the voltage and the current, you can use this wattmeter to get any of these values. And then we know the power factor is P over S. So we can get P, we can get S, and then we can use that to get Q, and then use P and S to also get the power factor. So that's really it for the theory. Now we're going to try some examples. So for the circuit on the previous page, assume that the voltmeter reads 200 volts and the ammeter reads 10 amps and the wattmeter reads 1.5 kilowatts, and that the load is a resistor and inductor in series. So let's draw a figure for what this looks like, and then let's try to find the real power, apparent power, reactive power, power factor, and components if the frequency is 60 hertz. So this is a copy of that figure from the previous page, but I'm now going to add in the values. Okay, so here's the source. And here's our ammeter that reads 10 amps. Here is our wattmeter that reads 1.5 kilowatts. And here is the voltmeter, which reads 200 volts. And then over here, we have our load, okay? Even though we have already seen in the problem statement that the load is going to be a resistor in series with an inductor. This is kind of ugly, but it's a resistor in series with an inductor. So I know resistor in series with the inductor already tells me something. That gives me a hint already that the power factor is going to be lagging and that theta V minus theta I is greater than 0. Okay. Are there any questions? Okay, So first, what's the real power? That's in the problem statement. So you should be able to give that to me now. What's the real power? You can come off of mute or you can type in the chat or I can start calling on people, which is my favorite. You know that. What is the
1.5 kilowatts?
Thank you. It's 1.5 kilowatts. Okay. All right. Now, for part B, the apparent power, which is also the magnitude of S, is just V times A. Okay, it's just the volts times the current. So that's going to be 200 V times 10 amps, which is going to be 2,000. And remember, the units for apparent power are volt amperes, or you can put 2 kVA. All right, the reactive power. The reactive power is Q. So Q is going to equal the square root of S squared minus P squared. The square root of S squared minus P squared is the square root of 2,000 squared minus 1,500 squared. What's Q? What's the numeric value for Q? And what are the units for Q?
1,322.88 var.
Okay, let's just say 1323, even though you're right. 1323 var or 1.323 kvar. Very good. Okay, next we're going to do the power factor. The power factor. Remember, the power factor is P over S, P over S. And it could be either leading or lagging, but we know it's lagging because we were told in the problem statement that the load is a resistor in series with an inductor, and an inductive load is lagging. So that's going to be 1,500 divided by 2,000. Which is 0.75 lagging. And then it says, what are the load components? What are the load components? We know it's a resistor and inductor, and we know that the frequency is 60 hertz. So for part E, omega, that's ugly. It's really hard for me to write on this thing. I know my handwriting's not the best, but roll with it. Omega is 2 pi 60 radians per second. Okay, so we need to find our impedance. So Z equals V over I. So this is magnitude because we don't know the phase angle yet, although I could get the phase angle. You know what? Let's go ahead and do the phase angle. We know the phase angle is going to be the arc cosine of the power factor. So I'll go ahead and do this. So Z is going to equal to V over I, where the angle is the arc cosine of the power factor. Okay, Z is V over I, and the angle is the arc cosine of the power factor. So this is going to be 200 over 10, and the angle, which is the arc cosine of the power factor, is 41.4 degrees. So the impedance is 20 with an angle of 41.4 degrees, and the units are ohms. Okay. So to get the impedance, it's voltage divided by current, and to get the phase angle, it's just the arc cosine of the power factor. I want everyone to take out your handy dandy calculator and convert the impedance into a real part and an imaginary part. So this is polar form. Convert the impedance to rectangular form. Okay. Convert the impedance from polar form to rectangular form. What is the impedance in rectangular form?
15 plus J 13.2.
Ohms, very good. 15 plus J 13.2 ohms. So that means we know that the resistance of the load is 15 ohms because it's the real part of the impedance. And we know that the impedance of the inductor is J omega L, which is J 13.2 ohms. So we know that omega is 2 pi 60. So J 13.2 equals J 2 pi 60 times L. J 2 pi 60 times L. So our inductor is 35 millihenry. So that part of the load becomes a 15 ohm resistor. In series with a 35 millihenry inductor. Okay, let me get the eraser. So we have a 15 ohm resistor and a 35 millihenry inductor to represent the load. Okay. Questions. Are there any questions? Example 2. For the following circuit, if device A receives 2 kilowatts at 0.8 power factor lagging, okay, so this is going to be 2 kilowatts, 0.8 power factor lagging, okay? Lag means that the angle is going to be greater than 0. And device B receives 3 kVA at 0.4 power factor leading. And device C is inductive. That means power factor lagging. And consumes 1 kilowatt and 500 var. So the other thing that these units tell us is what these values are. So up here, it was 2 kilowatts. So we know that that's P for A. So PA is 2 kilowatts. Down here, we have 3 kVA. So that means we know that S is 3 kVA, and that's SB. And over here, we have 1 kilowatt and 500 var for C. So we know that PC is 1 kilowatt and QC is 500 var. Are there any questions? So we're going to use our power triangles to solve this problem. We're going to use our power triangles to solve this problem. So what that means is for each of these elements of the load, I am going to draw a triangle and then use trig to find the values that I don't have so that I can find the power factor for the system. I need the total power. So for example, for load A, I have a triangle here. Where I know that P is 2 kilowatts and this angle here is positive. It's theta A. So theta A is the arc cosine of 0.8. Theta A is the arc cosine of 0.8. So that angle is 36.87 degrees. Are there any questions? So then if I want QA, if this is PA and I want QA, that's the tangent, right? So Q over P equals the tangent of theta A. Q over P equals the tangent of theta A. So QA equals PA times the tangent of theta A. Okay. So that means 2,000 times the tangent of 36.87. What is QA? What is QA? Oh, here we are. 1,500 var. All right. So that means that the complex power for A is 2,000 plus J 1,500 volt amperes. Okay, and we're going to do something similar for each of these. So now I'm going to do the same thing for B. So I'm going to draw the triangle. This one's leading. This one's leading. So I know that means I have a negative angle for this one. Okay, and I have 3 kVA. So that means my apparent power, which is here, is 3 kVA. And my angle, theta B, is negative because it's a negative angle. The arc cosine of 0.4. Negative the arc cosine of 0.4 is negative 66.42 degrees. For this one, I need PB and QB. So I need PB and QB. So PB is going to be 3K cosine. Yes.
A question for number A real quick, or part
Yes.
A.
Yeah.
Why is it Q plus P instead of square root of Q squared plus P squared? If it's like a triangle.
It is. That's the magnitude, right? So if I asked you to find S, which is the apparent power, then the magnitude of S would be, yeah. So remember, there's 2 S's here, Alfred. One of them is the apparent power. This is the complex power. The complex power is a complex number. The apparent power is a real number, and it's the square root of P squared plus K squared, right? So the magnitude of SA is the apparent power. So that's the complex power, and SA, which we know are, do we know what that is? Actually, we didn't find that number. We don't know what that is. Okay. Does that make sense?
Yes, it does. Thank you.
Okay, so PB is 3K cosine of theta, but we know that's just 3K times the power factor, which we already had. Hold on, I keep losing this thing. Thought I had made this bigger. There we go. So this is going to be 3K times 0.4. So that is 1,200 watts. And QB is 3K times the sine of negative 66.42 degrees. So QB is negative 2750 var. So the complex power is 1,200 minus 2750 volt amperes for B. Okay. Are there any questions? C, we know the real and the imaginary part, and we know it's positive because it's inductive. So we can actually go ahead and label the triangle. This is just 1,000 watts. And this is 500 var. We don't have to do any trig for this one. We just need to write down that the complex power is 1,000 plus J 500 volt amperes. So this is what I want you all to do. Take out your calculators and tell me what the total complex power delivered to the load is. So that would be SA plus SB plus SC. What is the total complex power delivered to the load? So you want to add together SA plus SB plus SC. Please do that now. You can type your answers in the chat. SA plus SB plus SC. 4,200 minus J, 750 volt amperes. Very good. All right. 4,200 minus J, 750 volt amperes. So to get the power factor for the load, we're going to convert that to polar form. That's rectangular form. We're going to convert that to polar form. So 4,200 minus J, 750 volt amperes converts to polar form as 4,266 with an angle of -10 degrees volt amperes. So now to get the power factor, you're going to take the cosine of -10 degrees. To get the power factor, take the cosine of -10 degrees. You can type your answer in the chat. Don't forget to put lagging or leading. What's the power factor? Remember, it's a number, and you want to put lagging or leading. 0.985 lag. Very good. Are there any, oops, is it lag? Wait a minute. Hold up. Is it lag or leading? It's leading. I'm only recording this meeting. For some reason, the transcription went off. Let me figure out what's going on with the transcription. 0.985 leading. Technology at its best. Okay, very good. Any questions?